Okay, so we're going to go ahead and finish up this chapter, which deals with alcohols today. So we've talked thus far in this chapter about various things with respect to alcohols. So first off, we dealt with nomenclature, various physical and chemical properties that we need to be aware of with respect to alcohols. We then talked about reactions that are going to produce alcohols. So we talked about hydration reactions of alkenes, right? We also talked about substitution reactions that would produce our alcohols. We then talked about how we could make alcohols from both ketones and aldehydes via reduction, right? So we talked about reduction via hydrides, via sodium borohydride or lithium aluminohydride. And then we also talked about reductions of ketones and aldehydes to produce alcohols via Grignard reagents, right? So Grignard reagents were going to form carbon-carbon bonds, so that's kind of what made them a special overall reaction. But again, that just involved producing an alcohol from a ketone or aldehyde via reduction of that ketone or aldehyde. And so now we're going to talk about reactions that are the reactions of alcohols to other things, right? So the first part of the chapter dealt with making alcohols. Now we're going to talk about the reactions that alcohols can undergo themselves. So part of this is going to be review. We're also going to learn a couple different reactions. And then we're going to kind of pull all of this together in the end and talk about synthesis and what this means long term for our various synthesis reactions. Okay, so first reactions that we're going to deal with in terms of alcohols are substitution reactions, right? So again, we've already talked about substitution. Ideally, this should be kind of review, but we will talk about a couple new reactions. So remember, we have two different mechanisms via substitution. We have SN2, which is the concerted mechanism. We also have SN1, right? We talked about the various factors that are going to influence both SN1 versus SN2 reactions. So the first reaction of alcohols that we talk about is an SN1 substitution reaction, where we have specifically tertiary alcohols. So remember, we've got our alpha carbon here. If we have a tertiary alcohol, if you remember, alcohols are terrible leaving groups, and we need a good leaving group for an SN1 based reaction. So one way that we could have taken a tertiary alcohol like this, taken that alcohol, made it from a bad leaving group to make it a good leaving group, is we could have protonated it, right? And so what we can do is for tertiary alcohols, we can add an acid. That acid can then protonate our alcohol, turning it into a good leaving group. And then that leaving group can therefore leave in a first step, because remember with the SN1 mechanism, this was our stepwise mechanism. So first step is loss of leaving group to produce our carbocation. That carbocation could then be attacked by the nucleophile, right? So the nucleophile here would just be the conjugate base of that acid. This was HBr. So the bromide ion is the conjugate base. It can attack the carbocation, and we end up with our tertiary alkyl halide as a product, okay? So that works for tertiary alcohols because, again, they will undergo that SN1 mechanism. But for the most part, that was not going to work all that well for our primary and secondary alcohols, right? Because for primary and secondary alcohols, we'll be undergoing that SN2 based mechanism. And so what we will find is for primary alcohols, and this is specifically for primary alcohols, we can see a very similar reaction where if we take a primary alcohol in the presence of HBr, so again, in the presence of specifically HBr, but this is an acid, it's going to have a first proton transfer step, right, which is going to take that alcohol, take it from a bad leaving group, turn it into a good leaving group. And then in a second step, the conjugate base, the bromide ion, is going to attack. This is going to now occur in a concerted process, right, where the nucleophilic attack occurs as well as loss of leaving group, and we could end up with our primary alkyl bromide. Now, this is very specific for only HBr. So if we have a primary alcohol, we react it with HBr, we will get our primary alkyl bromide as a product, but this will not work if we wanted something like HCl and the primary alkyl chloride, okay? So HCl will not react in this matter unless it is helped out So to make HCl essentially react in this very similar manner, we're going to need the presence of a catalyst, and that catalyst ends up being zinc chloride. So this reaction will occur for HCl, but it needs to be in the presence of the zinc chloride. And so the zinc chloride kind of serves this exact same type of process where it takes the alcohol, it turns it into a good leaving group that can then be attacked by the chloride ion or the nucleophile, okay? So in this process, again, this overall reaction, we're taking our primary alcohol and we're turning it now into a primary alkyl chloride, not the bromide. This is going to occur with HCl as long as that is also in the presence of the zinc chloride. So you need both of these to make this reaction occur. Okay, so that's for primary alcohols via substitution bimolecular mechanism. What about secondary alcohols? So I'm going to talk about a couple different reactions that are also going to be able to do this substitution-based reaction. The first one that we talked about, we've already dealt with before, right? So again, alcohol or that hydroxyl is a bad leaving group. One way that we could get around this to make it a good leaving group was to turn it into a tosylate, right? So this OTS. To do that, we use this tosyl chloride in the presence of pyridine, and pyridine is down here. The pyridine is just a solvent. And so first step, we take that alcohol, we turn it into tosylate. This is now a very good leaving group, right? And so now we can just attack it with our nucleophile, whatever we want that to be, right? So in this situation, this would be something like sodium chloride. That would be the source of that nucleophilic chloride ion, or if we wanted sodium bromide, that would be the source of that nucleophilic bromide ion, sodium iodide, etc., right? Now, it's important to note that if we're dealing with secondary alcohols, now we have to be aware of the stereochemistry of this reaction. For primary alcohols, this didn't matter because the substitution was occurring at a center that was not going to be chiral. It was on a chiral center. If we're dealing, though, with secondary alcohols, now we're going to be dealing with alpha carbons that are chiral centers. And so as a reminder for the SN2-based mechanism, what we see due to that concerted nucleophilic attack followed by loss of leaving group is inversion of configuration, right? So if we have a configuration, it's a good day for me spelling, I think. If we have, let's say, what is this? 1, 2, 3, 1, 2, 3. If we have an R, overall what we're going to end up with the product is an inversion of that configuration in S. The only thing I want to mention about this is that this reaction, taking that alcohol and turning it into that tosylate, does not change configuration. So we retain configuration here. It is only in the actual SN2-based process that we actually invert configuration. So it's this reaction going from here to here where we will actually see this inversion. Okay, so that is one way that we can take a alcohol, a secondary alcohol, and turn it into whatever alkyl halide or whatever nucleophilic reaction we needed to do. First turn that alcohol into a good leaving group, the tosylate, and then we'll react it via our SN2-based reaction. Now, that's one way. There are going to be two other ways to do this as well, depending on the overall product that we want to make. Okay, so I don't know why the book doesn't introduce you guys to these reactions when we go over substitution, but they don't, and they introduce it to you now. I don't know. My apologies. Another reaction that we can utilize, depending on the product that we want to obtain, is we can, again, take an alcohol. Again, this can be either a primary or a secondary alcohol. If we want the primary or secondary alkyl chloride as the product, then we can utilize this set of reagents or this set of conditions. So SOCl2 is something called thionyl chloride. And again, this is thionyl chloride in pyridine. That's the solvent. Usually when you're utilizing pyridine, maybe I did mention this before, it usually serves as a base as well, so just note that in any of these various mechanisms. So the idea behind thionyl chloride is that it's again going to take that alcohol, it's going to make it a good leaving group by reacting with the alcohol. I'm not going to undergo or talk about this mechanism, but just note that the first steps in this, so we have this step, and then this step. These steps are essentially just taking that alcohol and making it a good leaving group. And then at the very end, we'll actually have our SN2 base mechanism here, or our SN2 base reaction, where we have nucleophilic attack and then loss of that good leaving group. So if we have an alcohol and we want to turn it into an alkyl chloride, it's a primary or secondary alcohol, we can utilize this thionyl chloride and pyridine. And again, this is SOCl2. If instead we had a primary or secondary alcohol, and we wanted to turn it into the alkyl bromide, another reaction that we have is via this PB. So this guy is PBr3. This is phosphorus tribromide. See if I can spell phosphorus today for us. Tribromide. And it does a very, very, very similar reaction where it itself reacts with the alcohol to making it a good leaving group. And then it's also going to be the source of our nucleophilic bromide ion. And so after we make that bad leaving group into a good leaving group, we get nucleophilic attack and loss of leaving group in a concerted set. So all you need here is just the PBr3. For the thionyl chloride reaction, you need SOCl2 with pyridine. So you do actually need that pyridine as part of the overall reaction conditions. Okay, so those are a couple of different ways that we can take an alcohol, depending on its structure, and turn it into an alkyl halide. So with that, I want you guys to try this question. So we have a reactant over here. So note that this is an alcohol. Specifically, it is a secondary alcohol. And I want to turn it into this secondary alkyl halide over here on the product side. So what I'm asking you guys for is, what are the reagents that are going to get me from this secondary alcohol to this secondary alkyl halide in my products? So there are multiple answers to this, I will say that, but just be aware of kind of like the overall structure of your starting material, and then the overall structure of your product. And then we'll give you a break, so go ahead and try this one and then come back for the answer. Okay, so again, there are multiple solutions to this, depending on which reaction or which set of conditions you like the most. So again, we know that this is going to be an SN2 based mechanism. The reasons why we know this: number one, it's a secondary alcohol, so it's not really good for SN1 based conditions or SN1 based type of parameters. Number two, we see that there is inversion of configuration, and so we know that that has to go via an SN2 based mechanism. Okay. All right, so I'm actually gonna copy paste this guy a couple times. So let me get rid of this. I want to copy paste. I wish you could do it multiple times. Oh, that's not bad. Why would it not move that? Move. Do it again. Oops, I keep getting really close to that. And then one more time. Well, that can be the first one. Okay, so anyway, my bad. I should have done this before. So we know it has to be SN2 because, again, that inversion of configuration. We have just learned a couple new reactions that are going to allow us to do this. So the first one that we just learned was that thionyl chloride, right? So this can be SOCl2 in pyridine. Again, the first step is making our bad leaving group into a good leaving group. Then that's going to be attacked by chloride, so that will give us our overall product. Another way that we can go about doing this is we could utilize tosyl chloride to turn our bad leaving group into a good leaving group. So in our first step, we could do tosyl chloride and pyridine. That would give us this guy as a product, right? We could tosylate. Then we could take any type of source of that chlorine as a nucleophile, so some nice salt like sodium chloride, that could then attack in an SN2-based mechanism and give us overall our substituted alkyl halide, alkyl chloride. So that's one, that's two. Either of these are acceptable. Again, though, if we have one reaction followed by a second versus just one reaction overall, probably the one reaction is going to be better. You could also think, okay, well, what if we use that HCl reaction, right? So what if we use HCl with that zinc chloride as a catalyst? That is also an SN2-based mechanism. Now, the only problem with this one is that anytime we use this, zinc chloride is only going to be water soluble. So if we utilize this reaction, this also has to be water soluble. And if we count the carbons in this alcohol and think back to the physical properties of alcohols, right? This guy has more than 8 carbons in it. And so because of this, this is not going to be soluble in water. And so that's why it essentially excludes the zinc chloride-based mechanism, or this zinc chloride-based reaction. So this is not soluble in water. So that's why this would not be an acceptable answer. Okay, so another reaction that we are aware of with respect to alcohols already, this again is review, is elimination-based reaction. So this is going to take our alcohols and eliminate the leaving group, which would be the alcohol, as well as a proton, to get overall an alkene as a product. So one of the first reactions that we learned, or again with respect to elimination, we have two basic mechanisms. We have both the E2, or the concerted mechanism, versus the E1 mechanism, which was the stepwise mechanism. One reaction that we did learn was that acid catalyzed elimination for tertiary alcohols. This was via this E1, the stepwise mechanism. And again, it was taking an alcohol, a bad leaving group, it was putting it in the presence of an acid, which made it a good leaving group, and then that would undergo the elimination step to produce the alkene. Again, the overall reagents for that were our alcohol, of course, but again, to promote elimination, what we used was concentrated H2SO4 and then heat, and again that would give us our overall eliminated product, our alkene. Now, there are some issues with this, right? So this is good for tertiary alcohols. But one thing with respect to the E1 based mechanism is the fact that, again, when we talked about our alkene products, we had a couple of different options depending, right? So for E1, this always gave us the Zaitsev product. Regardless, it didn't matter. It was always going to be Zaitsev product. Again, Zaitsev was the more substituted alkene. For E2, we had an option between either Zaitsev or the Hoffman product, right? And so Hoffman product was the less substituted alkene. So for example, let's say that we had as a starting material, let's say that we had this guy as our alcohol, right? If we took this and we made the Zaitsev product would be this guy, right? Whereas we made the Hoffman product would be this guy. And so for E1, it is impossible to control between this or this. You will only ever get the Zaitsev product, right? And so if we need to control between which product we actually obtained, we have to utilize the E2 mechanism, right? So the E2 mechanism will give us the ability with which we can control, right? So to do that, let's say that we had our alcohol and we wanted to use this E2 mechanism. Again, we can't use acid to do this because, again, long term we have to add a base to go ahead and go through this reaction. So to take the alcohol and make it a good leaving group, we're actually going to have to utilize that tosyl chloride reaction again and turn this into a tosylate. So for E2, and again, this is for tertiary, secondary alcohols, we're going to take the first step, take tosyl chloride and pyridine. That's going to turn our alcohol into a good leaving group, so the tosylate group. Now, to control between whether or not we want the Hofmann or the Zaitsev product, we're going to do that by controlling which base we use, right? So if we use a strong non-sterically hindered base, something like sodium methoxide or sodium methoxide, that will give us the Hofmann product or the Zaitsev product, the more substituted alkene. But if we wanted the Hofmann product instead, my figures are getting pretty bad, which is the least substituted, then we'd want to use a sterically hindered base. So this would be something like terbutoxide. All right, so you have to consider that. If we don't care about, if we always want the Zaitsev product, and we have a tertiary alcohol, then we can utilize the E1 mechanism. The reagents here are concentrated sulfuric acid and heat. If we need a control, though, then the first step has to be, for this elimination-based mechanism, has to be tosyl chloride and pyridine first to take that alcohol and turn it into a good leaving group. We can then control the production of the base by using sodium methoxide or potassium terbutoxide to either produce the Zaitsev or the Hofmann product. Okay, so that's elimination. Now the question is, what other reactions can alcohols undergo? Okay, so in the first part of this chapter, we talked about how in our reactions that we're able to produce alcohols, we talked about how we could take a ketone or an aldehyde and we could reduce it, right? So we could have it gain electrons to produce an alcohol. And so if taking the ketone, reducing the aldehyde produces the alcohol, then the reverse of that, which would be the oxidation of the alcohol, would produce a ketone or an aldehyde, right? So now we're going to talk about these reactions. They're going to take an alcohol, they're going to oxidize it, and we're going to produce a ketone or an aldehyde, or either carboxylic acid as a product, okay? So now we have reagents that can do this. The question is, what can do this? What are going to be our products? And what type of starting materials are they all going to depend on? So first off, the overall product that we're going to get in this oxidation of alcohol reactions depends on the structure of the starting material. So if we start with a primary alcohol, so just note that this primary alcohol right now has an oxidation state. If we cut this bond up, it's going to get both of these electrons from the carbon-hydrogen, both of these electrons from the carbon-hydrogen, and then none of these guys up here. Then we have an oxidation state here of a -1. This guy has 2 carbon-hydrogen bonds, so anytime we oxidize an alcohol or oxidize anything, essentially what we're going to be removing is a carbon-hydrogen bond. It's those electrons. A primary alcohol has 2 of those, which can be removed. So this can undergo a first oxidation to the level of the aldehyde, or the oxidation state of the aldehyde. An aldehyde has 1, 2, 0, 1, has an oxidation state of a +1. But this aldehyde is also susceptible to oxidation, right? So it can be oxidized farther depending on the reagents that we use. So this is second oxidation to a carboxylic acid. Carboxylic acid has an oxidation state of a +3, right? So overall, we have a 2-electron oxidation here, and then another 2-electron oxidation to a carboxylic acid. If we start instead with a secondary alcohol, right? A secondary alcohol only has 1 carbon-hydrogen bond. It also has an oxidation state of a 0. Secondary alcohol can be oxidized to a ketone, which has an oxidation state of a +2, but there are no more carbon-hydrogen bonds in a ketone, which can be oxidized, right? So we're only going to see 1 oxidation if we have a secondary alcohol, and it's going to be oxidized to the oxidation level of a ketone. So now the question is, well, what reagents are going to do this, right? This oxidation of these alcohols to either the aldehyde, carboxylic acid, or the ketone. And the answer to that is on the next slide. So the reagent that's responsible for these oxidizing reactions, one of them at least, there's going to be a couple. The first one we talk about is chromic acid. So chromic acid has the molecular formula of H2CrO3, and it's given, the structural formula of it is given here. So note just quickly that chromic acid is extremely toxic, and it's very, very, very reactive, very oxidizing. So the book actually goes through 2 other potential reactions or reagents, sets of reagents that are much more benign and I guess better for the earth. I don't go over those though, so we're just going to imagine that we're going to use chromic acid and going to be very careful anytime we do any of these reactions. So we're only going to focus on chromic acid as well as PCC, which I'll talk about in the next slide. Okay, so the main oxidizing agent is this chromic acid. There are 2 different ways that we can prepare it. So the first one is taking chromium trioxide. So chromium trioxide has a molecular formula CrO3. This is going to be in acidic conditions in acetone that will form chromic acid. Another potential way that we can do this is to take sodium dichromate. So sodium dichromate has a molecular formula of Na2Cr2O7, and its structural formula is given here. We're going to take sodium dichromate in an aqueous acidic solution, and that will also produce chromic acid, right? So we have 2 different possible sets of reagents that are going to produce our oxidizing agent, chromic acid. Okay, so chromic acid is very, very, very reactive. It's very oxidizing. So for chromic acid, unfortunately, if we do have a primary alcohol, it will take that primary alcohol and completely oxidize it to the carboxylic acid. So unfortunately, if we use chromic acid with a primary alcohol, we cannot obtain the aldehyde intermediate, or the only single oxidation aldehyde product, right? We're only going to get the carboxylic acid. Now, the question is, of course, which it always is, but what if we wanted to obtain the aldehyde, right? What if we didn't want the carboxylic acid? And so the answer to that is we have to use a different reagent. We can't use chromic acid. And that reagent particularly or explicitly is something called PCC. And so the answer to that is we're going to use a different reagent. This is called pyridinium chlorochromate, PCC for short. And this is also going to be in the solvent methylene chloride. So if you took PCC, you had a primary alcohol, this would oxidize it to the aldehyde. So PCC is a little bit less reactive than chromic acid. It stands for this pyridinium chlorochromate. So this is the overall structure of PCC. In this reaction, it's going to be PCC, which you can utilize the acronym for that, but the solvent here is methylene chloride, so this is CH2Cl2, PCC. Now, PCC is a little bit less reactive, so it is more selective, and it will take a primary alcohol, and it will oxidize it to an aldehyde, right? So it won't go to full oxidation to the carboxylic acid. Now, for the secondary alcohol, remember we only had 1 hydrogen, so this was our primary alcohol. If we want the carboxylic acid, we'll use the chromic acid. If we want the aldehyde, we'll use the pyridinium chlorochromate, the PCC. Now, if we had a secondary alcohol, we can only oxidize that once anyways to a ketone. So for secondary alcohols, you can use either the chromic acid or the PCC. Depends on whatever you want to do. Okay, so go ahead and try this one utilizing the new reactions we've just learned. So we've got an alcohol. Specifically, this is a primary alcohol, and we're reacting it with that pyridinium chlorochromate, so PCC and methylene chloride as a solvent, and I want to know what is the product for this overall reaction. So go ahead and try this one and then come back for the answer. Okay, so the important thing to note right now is, number one, you're dealing with an alcohol. The structure of the alcohol is also important. It is a primary alcohol, so there are two potential carbon-hydrogen bonds that can be oxidized. And then it's also important to notice the reagent, right? So if this was chromic acid, or if this was the things that make chromic acid, so Na2Cr2O7, H2SO4, and H2O, then the overall product of this reaction would be the carboxylic acid, right? Because this guy is super strong. It's a great oxidant. It's going to oxidize a primary alcohol all the way to a carboxylic acid. PCC, though, is different, so it's not as strong of an oxidizing agent. And so this one, you have to just note that this is going to oxidize a primary alcohol to, damn it, what did I do? To the aldehyde as opposed to the carboxylic acid. And so then, again, this alcohol is on this first carbon here. That's what's going to turn in to the carbon-oxygen double bond of the aldehyde, and then one of those hydrogen is still going to be left off to the side. So in this reaction, we are oxidizing off one of these guys. We are still left with this and this and this. And again, this turns into the carbonyl, the C O double bond. All right, so that's it. So the final product here is the aldehyde, and you just have to recognize that the fact that PCC is not as strong of an oxidizing agent as a chromic acid, and that it's only going to produce an aldehyde from a primary alcohol. Okay, so with that, that's all of the new reactions we're going to learn in this chapter. So now we're going to kind of bring them together and talk about how this is going to change our approach to synthesis or not change our approach, or how we're going to be able to incorporate these new reactions into our overall synthesis-based strategies, right? So as a reminder, last chapter, we talked about synthesis. And again, with respect to synthesis, we're talking about, hey, we're giving you a reactant, we're giving you a product, and we're asking, how do we get from A to B, right? How do we get from reactant to product? Frequently, especially as we add more and more reactions, these syntheses that we're going to be proposing are going to be more than just 1 to 2 steps, right? We're going to now be involving 3 to 4 different reactions and taking our reactant A and getting to B overall. And so we're going to talk about how, or we can kind of compartmentalize these reactions, and then how we're going to kind of organize our thoughts as we continue to approach synthesis-based problems. All right, so as a reminder, as these synthesis problems get harder, as it takes more and more steps to get from A to B, the best method about going about doing this is using that retrosynthesis approach, where instead of trying to get here to here, we actually try to go in reverse. So we say, hey, if I have B as my final product, what types of things can make B? And then what types of things can make the thing that I've just wanted to make? And then how do we get from A to the thing that we're at? All right, so we're going to utilize retrosynthesis as we go through these synthesis problems. Okay, so again, with respect to these synthesis-based problems, it is very helpful to try to organize all of the reactions that we have available to us at this point in time. And it's also very helpful to keep in mind the 2 basic questions that we're going to be asking, which is what has happened to the carbon skeleton, and then what has happened to the functional group. Has it changed identity? Has it changed location, etc.? We're going to talk about functional groups first, and then we'll talk about the carbon skeleton. But just as a reminder, reactions that we've already talked about, we already know how to go from an alkyne to an alkene to an alkane, and reverse, right? We know how to take an alkane to an alkene to an alkyne. Just as a note, with the stuff that we've learned in this overall chapter, this process of going from an alkyne to an alkene and then from an alkene to an alkane is a reduction process, right? We will be reducing the alkyne to the alkene, alkene to the alkane. Therefore, in going from the alkane to the alkene, this is an oxidation process. And then from the alkene to the alkyne, this is an oxidation process. Okay, so you guys can review these reactions. We've already covered them in detail, right? So if we want an alkyne and we want to reduce it to the alkene, we have two possibilities. We have Lindlar's catalyst if we want specifically the cis alkene, and then we have that dissolving metal reaction or dissolving metal reduction if we want the trans alkene. If we have the alkene, to make an alkane, all we have to do is that catalytic hydrogenation, which is hydrogen in the presence of a catalytic metal like platinum. In the reverse, if we had an alkane and we needed to make something with it, right, the first thing we need to do is functionalize it. We've only been given one reaction to do that. That was our radical bromination reaction. So that was bromine in the presence of light, H nu. That would give us our alkyl bromine. And then with that alkyl bromide, if we wanted to turn that into an alkene, we could do that via an elimination process. So that would be an E2 process, and we would just need some sort of strong base, like sodium methoxide. So that's here. If we have an alkene and we want to make the alkyne with it, we would first need to halogenate it, right, to form the dihalide. So we'd be having that halogenation reaction. Specifically, again, this has to be in the presence of some non-nucleophilic solvent. We would get the dihalide as a product of this, and then with that dihalide, we would need to undergo two separate elimination reactions, right? And so we used that sodium amide. That amide was a really, really, really strong base. We used an excess of it to undergo those two successive eliminations. At the end of this, we would have ended up with a deprotonated alkyne, right, the alkanide ion, and so we have to add water in that last step to protonate it and end up with our protonated alkyne. All right, so again, these reactions we've already covered. Now, new things that we've learned, right? We've now learned how to take a alcohol and oxidize it to an aldehyde or a ketone, right? So if we have a secondary alcohol, we can oxidize it to a ketone via our oxidation reaction. So that was our chromic acid. So we could utilize sodium dichromate with sulfuric acid and water. We could also conversely use CrO3, again with a proton source, so H3O plus and acetone. That would oxidize our alcohol to our ketone. So this is this or the chromium trioxide. We could also still use, so this is, let's say, one option, one choice. So this is one choice, this is one choice. We could also utilize that PCC, and that was in pyridine. That would, all three of those are options. So take the alcohol, secondary alcohol specifically, and oxidize it to the ketone. We could also take a primary alcohol and oxidize it now to the aldehyde. We cannot use the chromic acid for these guys, so the only thing we are able to utilize for the primary alcohol to the aldehyde is the PCC. Oh, it's not in pyridine. That's my mistake. See how easy it is to get confused? Pyridine's in there, but it's part of the PCC. So this was in methylene chloride. So CH2, so again, with the primary alcohol, we have to only use PCC if we want the aldehyde as a product. We could also take that primary alcohol, and if we wanted to oxidize it to the carboxylic acid, to this guy, we could use that with our chromium, our sodium dichromate, or the chromium trioxide. So this could also be either Na2Cr2O7, H2SO4, and water, or another option, or I don't like using 1 and 2 because I think that's confusing, or the CrO3, H3O plus, and acetone. And this is a primary alcohol to the carboxylic acid. I don't think you'll see this because we don't get too far in terms of carboxylic acids, but just be aware that is also a possibility. Now, we also talked about how we can reduce an aldehyde or a ketone to an alcohol. That was using our reducing agents like lithium aluminum hydride or sodium borohydride. And again, if we use lithium aluminum hydride, that occurs in one step. It's a very, very strong reducing agent. And then in the second step, you have to add in water to get, you end up with the alkoxide as a product. To get the protonated alcohol, you need to add water in a final step. And I would go back and review those reactions at the beginning of this chapter as a reminder. Okay, so now it's kind of helpful if we kind of organize everything in terms of functional groups. And the way this chart is arranged, it's really nice because it kind of, organizes all of these reactions and their reagents and what they're going to, convert things to. But also what's really nice about this is it keeps track of oxidation states. So just note that, again, as we move from the alkyne to the alkene to the alkane, overall what we're doing is we're decreasing the oxidation state. We're reducing these carbons, right? And so overall this process is a reducing process, and then the reverse process is an oxidation. But just another thing to note is that the carbons in an alkyne and the carbon in the ketone versus in an aldehyde, these guys all have the same exact oxidation state, right? So in moving from an alkyne to a ketone or an aldehyde, which we do know how to do, that's a hydration reaction, these guys don't change oxidation state. So this is just like a basic acid-base reaction. Conversely, or very similarly, not converse, but alkenes and alcohols and alkyl halides, all of these guys also have the exact same oxidation state, right? So we're not using any type of oxidation or reduction to move between an alkene or an alcohol or an alkyl halide. And then finally, alkanes, they're the most reduced form of carbon, so they're kind of out here by themselves. So you can kind of keep track of this in terms of oxidation reduction. If we're moving from an alkane to an alkyl halide, we're changing oxidation state. So overall, it's an oxidizing process. Same thing between an alkane and an alcohol, and vice versa. So consult back to this. This is helpful. And again, it helps organize some of these reactions for you, so you don't necessarily have to, you have to memorize everything, of course, but you get what I mean. This is a nice, helpful hint. You could even go through and kind of like, maybe like, not outline, what is it called? Oh, white out. You could white out things, right? And then try to test your memory of how to get between A and B and C by writing in the actual reagents above and below the arrows for each individual reaction. Okay, so then the last thing we need to just kind of remind you guys of in terms of synthesis with respect to this chapter was the fact that we also did learn how to create a carbon-carbon bond, right? So we now have two means by which we can extend a carbon chain. So the one that we learned this reaction or this chapter was the reduction of an aldehyde or ketone via a Grignard reagent, right? So if we had an aldehyde or a ketone and we utilized a Grignard reagent, remember that this Grignard reagent made a very, very, very strong carbon nucleophile, and so it attacked the aldehyde and the ketone, which produced the alcohol. Again, this is a reduction process overall. The original Grignard reagent was a very, very, very strong nucleophile. It was also a very strong base, right? And so we had to undergo that reaction first. The initial product was going to be the alkoxide ion, so it would be the alcohol with the H not there, right? The negative charge on the oxygen. And then in a separate reaction, we had to add in water to protonate that alkoxide. So in these Grignard reagents or these Grignard reactions, they have to happen in two separate steps because the Grignard reagent and the water are not, aren't allowed to be with each other because, again, the water would just react with the Grignard reagent and ruin it, essentially, right? We just end up with the alkane as a result as opposed to the carbon nucleophile, which is what we want in this overall reaction. So in the first step, you have your Grignard reagent, forms a carbon-carbon bond and extends the carbon chain. In the second step, you add in water to protonate the alkoxide so that you end up with the alcohol at the end of the day. Okay, so this was possible for both the ketone, so reduction of a ketone, as well as the aldehyde. And just as a reminder, if you had an ester, the ester could undergo two separate Grignard reagents, right? So if you had excess of your Grignard reagent, it would undergo a first reaction, which would kick out the ether portion, and then it would produce a ketone at the end of that, or an aldehyde at the end of that. That aldehyde would then be susceptible for further reduction, so you could actually essentially end up with two reactions with your Grignard reagent and the addition of two new carbon-carbon bonds. Okay, so with that, let's talk about synthesis. Okay, so I'm going to go through these two problems, and I'm going to kind of propose or show you how I think about these and how I go about solving them. And then I have three that I want you to do on your own. And then, of course, I'll have the answers posted. But I'm going to do these two, and then we'll talk about the next slide in a second. Okay? All right, so the first one I'm going to move because I don't have a lot of room here. So I'm going to copy this guy, and I'm going to move it over here. And we'll go here. Oops. Okay. All right, so first step I'm going to do in trying to solve any of these types of problems is, again, asking the same questions that I've asked before, right? What's happened to the carbon chain? What's happened to the functional group? So in doing that, or in answering that, I'm going to count my carbons first. I have 1, 2, 3, 4. So we have 4 carbons as a reactant. I then go to 1, 2, 3, 4, 5, and we have 5 carbons as our product, right? So what's happened here is we've extended the carbon chain by 1. So extended carbon chain. We've also changed the functional group, right? So in our reactant, if we go 1, 2 here, we had an alkyne in between carbons 1 and 2. If we go 1, 2, we now have a ketone at carbon 2, pardon me. So we don't necessarily change the location, but we do change the identity of the functional group. We go from an alkyne to a ketone. Okay, so first off, I'm going to at least attempt to answer this in terms of a retrosynthetic methodology, right? So I'm going to go in reverse and say, hey, this is my product. What things could produce my product, right? So one thing, or one reaction we've already talked about, we have a ketone. This is a ketone, right? One thing that could produce this overall is the oxidation of a secondary alcohol, right? So we could make this ketone via, God, I hate when via the oxidation of this alcohol, right? And so we know we can do that. Again, we have a couple options here. So I'll go ahead and just use the sodium dichromate, or chromic acid, long-term H2SO4, and H2O. Okay, so we can do that, right? So if I have a secondary alcohol, I can oxidize that to my ketone. Now the question is, again, thinking the fact that I'm going to need to add a carbon, right? I'm going to specifically need to add a methyl group at this position. The question would be, well, then what could make this alcohol, right? And if I think about it, I could say, okay, well, I can make this alcohol via the reduction of an aldehyde with a Grignard reagent, right? So if I had a 4-carbon aldehyde group, so if I said I had 1, 2, 3, and then this guy was my carbonyl, and this was a hydrogen, so again I have 1, 2, 3, 4 carbons, and I took this guy and I added to it in a first step just that methyl Grignard reagent, right? And then in a second step I added to it water to protonate the resulting alkoxide. This is exactly what I would get as a result, as an alcohol, right? Again, with the Grignard reagent, we have an aldehyde or a ketone. We're going to take this guy, which ends up being a really, really, really strong carbon nucleophile. It's going to attack this. It's going to essentially push out those pi electrons. And at the end of the day, we're going to be making a bond between this guy and this guy, right? So we'll have this that's negatively charged. We'll now have this new methyl group, and we'll have this hydrogen all at this carbon. And then to get this to be protonated, this is when we add in that water in the second step, so that we end up overall, I've gone in reverse, of course, water, so that we end up overall with this. All right, so now at the end of this, we have this 4-carbon aldehyde. And the question should be, well, okay, we have 4 carbons. We don't have to worry about adding another carbon. Is there any way that I could get from the alkyne to the aldehyde at this point in time? All right, and so again, this requires that you know how to get from an alkyne to an aldehyde. This, if you kind of remember back in the day, this ended up being a hydration reaction, right? So specifically, we were trying to hydrate this in an anti-Markovnikov fashion. Anti-Markovnikov. Because again, the initial product that we would get was that enol, right? That ketone or aldehyde with the double bond. But then, no, it was a double bond with an alcohol, but then that would polymerize into the aldehyde. So this was anti-Markovnikov hydration. And so the way to do that was very similar to the hydroboration oxidation of the alkene. We couldn't use BH3. Instead, we had to use that 9-BBN. And then in the second step, it was that oxidation step. We had H2O2 and then sodium hydroxide, right? And so that was a way to get from the alkyne into the aldehyde. Okay. So that's it, right? I mean, that does it. We take the 4-carbon alkyne, we convert it to the aldehyde via that hydration reaction, that anti-Markovnikov hydration. Then we'll react with our Grignard reagent. We'll add in just 1 carbon. We'll add water to end up with our protonated alcohol, and then we'll take that protonated alcohol and we'll oxidize it via our chromic acid to get our 5-carbon ketone as a result. So overall, we have a 9-BBN. In the second step, we've got H2O2, and sodium hydroxide. In a third step, we've got the Grignard reaction, so CH3, MgBr. In a fourth step, we have water. And then in a fifth step, we have that oxidation reaction. I wonder if I have enough room. It's kind of the only, okay, well, hydration, anti-Markovnikov, I'll rewrite that. So in that fifth step, we have our chromic acid reaction. There's a couple of options here. So we have Na2Cr2O7, H2SO4, water. You could also use the PCC, methylene chloride. You could also use the CrO3, H3O+, and acetone. There are a couple different options there. And again, this was hydration, anti-Markovnikov. Okay, so one thing I want to note here really quickly is that you could have attempted to go a different route with this, right? So again, we have 2 different means by which we can form a carbon-carbon bond, by which we can go from 4 carbons to 5 carbons. The other route that you could have attempted to take was say, okay, I've got this alkyne, right? I'm going to deprotonate it with a strong base, right? So my first step, I'm going to use that strong base, sodium amide. That was going to give us that acetylide ion, right? So we would have ended up, if I can draw correctly, with this, which is a nice strong nucleophile. We could have then had this attack a methyl iodide or just a methyl alkyl halide. So a CH3, let's say I. And again, these guys would have reacted via an SN2 base substitution reaction to extend the carbon chain as well. All right, so this is what you would have been left with in terms of the product of this first reaction. And then you could have said, okay, well, I can also hydrate this into a ketone, right? And so you could have said, oh, if I undergo a Markovnikov hydration here, then I will end up with the, again, enol as a product, but that tautomerizes into a ketone, right? And you can say, oh, there I am, I'm done, right? That's my reaction. I have a acetylide. I'm going to produce the acetylide ion. It's going to undergo a substitution reaction to produce my 5-carbon chain, and then I'm going to hydrate that to end up with my ketone. Now, there's only one problem to that, and that's the fact that this is an internal alkyne. And so with internal alkynes, there is no way that we can control where the water attacks, right? So if the water attacked here, right, and you ended up with the alcohol there, then that would have tautomerized into this product. But if instead you had hydration here and the OH went here instead, then you would have ended up with this product, right? And so if you do deal with an internal alkyne and you try to hydrate it, you're going to get these mixtures, this mixture of products, which is not ideal because only one of these is the thing that we want, right? So because you would have gotten this mixture, this would not have been a useful synthetic strategy, right? Because again, half of the stuff that you make isn't actually what you want, and it would be very difficult to try to isolate these guys. So the initial synthetic strategy that I highlighted here, this would be the way to go. There is a wrong answer essentially to this. Okay, well, that's one. Let's go ahead and go through two, and then we'll see what type of mistakes I make. So we have here a nice alcohol, right? We've got a 1, 2, 3, 4 carbon alcohol. We turn this into a 1, 2, 3, 4 carbon alkane. So we have a secondary alcohol, and we turn this into an alkane. So we reduce it long term if we think in terms of oxidation reduction. Okay, so we know that we're going to have to deal with a reduction step at some point in time. The question is how, right? So how do I make an alkane, or what type of reactions are available to me, right? I don't have a reverse of like, I guess, of defunctionalizing an alkane, right? Because like we can take an alkane and we can be like, oh, I'm going to put a halogen on it, right? We have that radical bromination, but there's no reverse to this reaction. The only real reaction we have available to produce an alkane at the very, very, very end is to reduce either an alkene or an alkyne, right? So we do have a reaction where we can take an alkene and we can make an alkane, right? And that is that catalytic hydrogenation, or catalytic reduction at this point. Now we can use the word reduction. So now the question is, okay, well, we can do that. Is there any way that I could take a secondary alcohol and produce an alkene, right? Is there any way to go ahead and piece these two together? And ideally, you should be able to see, well, yeah, you could eliminate the alcohol, right? If you underwent an elimination reaction, that would give you the alkene, but there's a couple things to note here, right? If this was tertiary, that would be great. We just do it in one step. It'd be acid catalyzed. If we did that, though, we would only get the the Zaitsev product, whereas this may necessarily require that we get the Hofmann product, right? If this is our leaving group, or whatever happens to this becomes our leaving group, then there are two possibilities about what type of alkane or alkene we can produce from this, right? If we react with the proton here, then we get the Zaitsev product. If we react with the proton here, and then we get the Hofmann product, right? We want the Hofmann product. Or actually, we don't. It could be Zaitsev. There's nothing wrong with that, right? I wonder why I thought that. So it could have been that, or it could have been that, right? Which is fine. That could also be the alkene that we are coming from. Again, though, I would have it associated with this bond, or this carbon at some point, because again, this is our functional group. It's got to leave to produce this overall alkene. Now, again, if it's tertiary, then this is a single step elimination. It's acid catalyzed, it's great. Unfortunately, this is a secondary alcohol, so we can't use that acid catalyzed E1 mechanism. Instead, we have to use an E2 mechanism for elimination. And again, this relies solely on the fact that this is a secondary alcohol. So the only way that we can do that is to first turn this from a bad leaving group into a good leaving group, that tosylate. And then from there, we can eliminate that leaving group, right? And so here, to go from the alcohol to the tosylate group, we need tosyl chloride and pyridine. And then to go from our tosylate to our eliminated product, this specifically is Zaitsev. So if it's Zaitsev, then we can just use any non-sterically hindered base. So this is something like sodium methoxide or sodium methoxide or whatever you want to use. I would use a methoxide though, just because Naomi is a lot easier to remember. And so yeah, this one was not too bad. We had our first step was taking the alcohol, turning it into a tosylate. So this was tosyl chloride and pyridine. In a second step, we eliminated it with a strong non-sterically hindered base. You do have to use methoxide or a non-sterically hindered base. You can't use tert-butoxide here because that would have given you, well, you could, and then Hoffman, you still reduce it. So it doesn't really matter. And then finally, you got hydrogen and source of some sort of catalytic metal like platinum, and that'll give you the alkane as a result. Okay, so with that, go ahead and try these three. So attempt to propose efficient synthesis for the following. So again, give these things some thought, come back, and I will reveal the answers to you. Okay, so let's go ahead and start on this first one. So again, the first thing I'm going to do for both of these is count carbons, see what's happening to the carbon chain. So when I do that, I've got 1, 2, 3, 4 carbons as a reactant, and then I've got 1, 2, 3, 4 carbons as a product. So nothing's happened to the carbon chain. So I don't have to worry about Grignard, I don't have to worry about the alkylation reaction. All right, so then the question is, okay, I'm going to try to do this in reverse, and this one's actually kind of an easy one, so you may be able to see going in the forward direction. But my question is, okay, so how do I make a alkene, or what are some of the ways that we've learned how to make an alkene, right? So especially coming from the fact that we do have a functional group. It is an oxygen-based functional group. It's an aldehyde. It is at carbon 3, or if you count it 1, 2, 3, we'll count that 3. And that's been replaced by a double bond. I have to imagine that we have to go through some sort of alcohol intermediate, right? Because again, to get, there could, I mean, yeah, it would be kind of pointless to try to make, could you make a triple bond out of that? No, you could not. So it has to go through an alcohol intermediate. So then, if that's the intermediate, and if I go and try to draw that, so we've got some sort of alcohol here, right? Because we can already go from this to this. We know how to do that. Again, this is a hydrogen. Then to get from this to this, we have to undergo an elimination reaction. Again, though, this is a primary alcohol, though, right? And so to do that, we would have to go through some sort of good leaving group intermediate, so a tosyl chloride, and then we could then go to make this. So ideally, that's kind of essentially how we're going to go about this, right? We know how to make our alkene from our alkane with this tosylate leaving group, right? This is just going to be just a basic E2 reaction, so we could use something like sodium methoxide to do this. To get from the alcohol to the tosylate, we just need tosyl chloride and pyridine. And now to get from the aldehyde to the primary alcohol, we need a reducing agent And a common one that we frequently use is lithium aluminum hydride. So you could say LAH. And then you always have to follow that with water. Another way that we write lithium aluminum hydride is LiAlH4. That's the actual chemical formula for it. Again, followed by water. So yeah, the reduction of the aldehyde to the alcohol is first. Once you're in the form of the alcohol, then to eliminate that, then you do need to go through that tosyl chloride step to make that alcohol into a good leaving group. And then once it's a good leaving group, you can just eliminate it. There was no real stereochemical issues with this reaction, right? If this is the alpha carbon, there's only one option for a beta proton, right? So there's only one stereochemical outcome for this product. So that wasn't the best explanation, but again, if I kind of rationalized it, we had an oxygen-based functional group at carbon 3 that turns into an alkene between carbons 2 and carbons 3, right? So we're going to have to undergo an elimination at some point in time. And then the only way to get into a situation where we could do an elimination reaction is to reduce this aldehyde to an alcohol, right? We don't have reduction of an aldehyde to anything else. We couldn't have reduced this into like an alkyl halide. We don't have any type of reaction for that, right? So this had to go through an alcohol intermediate or an alcohol in this reaction pathway, and then once it was an alcohol, we could switch that for a good leaving group and then eliminate after that. Okay, so then I'm going to move on to B. Let me go ahead and highlight everything. So first step is lithium aluminum hydride. Second step is water. Third step is tosyl chloride, pyridine, and of course I ran out of room on the bottom half of my arrow. Fourth step is sodium methoxide, or any strong base. Okay, so we'll move on to B. So this one's a little hard. It's going to take quite a few different steps to get there. We're taking an alcohol though, and again, counting carbons first. We've got 1, 2, 3, 4, 5 carbons. I don't care about that methyl that comes off. Just the basic parent chain has 4 carbons. Okay, I'll just say there's 5 carbons, right? If we go over here, we've got 1, 2, 3, 4, 5, 6, right? So we do extend that parent chain, that backbone, by 1 carbon. Right, so we go from an alcohol, which is at, let's see, this is at carbon 3 on the parent, to a ketone, 1, 2, 3, 4, at carbon 4. So we change the location of the functional group. We also change the identity of the functional group. We also add a carbon. So those are all things to keep in mind. Okay, so especially with respect to after coming out of this chapter, if I try to go in reverse here, one of the big things I'm going to note is that I have a ketone, right? I have a carbonyl, and I'm going to have to add a carbon at some point in time. So likely there's going to be some form of either an aldehyde or a ketone to an alcohol back to an aldehyde or a ketone, right? So, for example, if I had started, or if I had said, okay, this guy can be made from the oxidation of this, right? Then I could say, well, okay, I could have produced this alcohol via that Grignard reaction, right? If I had taken a 4-carbon aldehyde, so 1, 2, 3, 4, with this being an H, and this, and I had reacted it with our Grignard reagent, right? So CH3MgBr, that would be number 1. Again, that nucleophilic carbon is going to attack that carbonyl carbon, right? It's going to form a new bond, or a new carbon-carbon bond, which is this guy. And then in the second step, we add water to protonate that alkoxide, and so we would end up with that alcohol, right? To take that alcohol, which is a 1, 2, 3, 4, 5 backbone carbon alcohol, and oxidize it to the ketone, that's fairly simple. We can just use PCC in that methylene chloride. We could use our chromic acid. There's a lot of different means by which we can oxidize an alcohol to a ketone. Right, so that's going to be kind of common. If you have some sort of like, long-term aldehyde ketone finished product, you've added a carbon somewhere, it's probably going to have gone through some sort of aldehyde ketone to an alcohol to an oxidation to an aldehyde ketone. Okay, so then next question is, okay, we start with an alcohol. 1, 2, 3. We start with an alcohol at carbon 3. We end up in this part with an aldehyde at 1, 2, 3, 4, right? And so now the question is, well, we've finished the carbon, right? We've added the carbon. Now the question is, okay, we're changing the identity as well as the location of this functional group. And so we know how to change the location of a functional group. That usually goes through some sort of elimination followed by addition, right? The problem with this guy is, though, if we're going to do that, an elimination followed by an addition, is that if we were to take this and try to do an elimination reaction now, it wouldn't give us anything. We have a secondary alcohol, and we can only use acid catalyzed elimination for tertiary. So the first thing we have to do is to take this and we have to change this again into a tosylate group. So now this will leave if we do an elimination reaction, right? So this is just tosyl chloride and pyridine. Now we can eliminate, but note that when we eliminate, we don't want to make the double bond here, right? Because the only thing we can add to that would just put something at carbon 2 or carbon 3, but we need something at specifically carbon 4. And so we want to make the double bond here, right? This is where we want the double bond to go long term, okay? And so again, this is not the Zaitsev product, but this is the Hofmann product. And so we have to be very specific about the base that we use here. We need a bulky, sterically hindered base like turret butoxide, so that we can ensure that we get the Hofmann product, and we can ensure that that double bond is between carbons 3 and carbon 4. So then we can add something and put that new thing at carbon 4. Right, so if we do that, we end up with this guy. And so now the question is, well, how do I get from this to this? Right, now we can add and put something at carbon 4, right? If we added something in a anti-Markovnikov fashion, it would go here as opposed to here, which is what we want it to go. But now the question is what, right? So what is going to be the go-between between an alkene and an aldehyde? So the answer ideally should be an alcohol, right? We know how to oxidize an alcohol to an aldehyde. And so can we add an alcohol, or can we do something to add to make sure that we end up with an alcohol at the end of our addition reaction? And so the answer to that is yes, we can have this guy, we can hydrate this, right? But we have to hydrate in a very specific fashion, right? We have to hydrate this in a anti-Markovnikov fashion, so the OH goes at carbon 4, because again, that was the whole purpose of this. Once we have, let me write anti-Mark. Once we have the alcohol at carbon 4, though, just to get to the aldehyde, that's a single step reaction, right? All we need to do is oxidize this. And so again, since this is a primary alcohol, we do have to be very specific in the reagent that we use now, right? There's only one reaction that will take a primary alcohol and turn it into an aldehyde. And that was specifically that PCC and then in the methylene chloride. You cannot use chromic acid for this because it would oxidize it all the way to carboxylic acid. Okay, so then after that, well, that's it, right? So if we have the aldehyde, we react with our Grignard reagent, it adds on the methyl group. We still have our alcohol at carbon 4, and then all we have to do is re-oxidize this with PCC. For this one, because this is a secondary alcohol, you could have also used the chromic acid. So again, this is Na2Cr2O7, H2SO4, or water. There's other options. You could use either this or this, but this one, for the primary alcohol, this has to be the PCC. Okay, so now if I collect everything, our first reaction here was turning that alcohol from a bad leaving group into a good leaving group. It's going to be tosyl chloride and pyridine. Second, we're going to eliminate that to produce the Hoffman product as our eliminated product. So we have to use a bulky base here, tertbutoxide. Then we're going to add to that alkene. We're going to hydrate it, but we're going to hydrate it in an anti-Markovnikov fashion. So for this one, this was that BH3 in THF. This is that hydroboration oxidation. So it was this BH3 in THF. This is 1, 2, that was followed by oxidation, so H2O2 NaOH. So we do that, so this is 4 H2O2 NaOH. 5, we do our Grignard reaction. So we have CH3 MgBr, and then 6 we have water. And then finally, we have our alcohol. It has 5 carbons in the backbone. So now we're going to oxidize that. And I'm going to use this nice PCC because it's nice and easy to write. So CH2Cl2. Oh wait, we didn't oxidize this guy. Oops, I missed a step. My bad. Wrong. This becomes before. So we hydrate, anti-Markovnikov, and then if I highlight this, we have to oxidize first. So this is 5. So PCC, CH2, Cl2. Then we do our Grignard. CH3, MgBr, 7 H2O. And then 8, we go back to PCC, CH2, Cl2. Okay, see, this is not so bad. 8 separate reactions, it's not a big deal. Okay, so then finally, we go to this last one, and we do the same thing. First thing we do is count carbons. We say 1, 2, 3, 4. We say 1, 2, 3, 4, 5. So we add a carbon. So we have 4, we have 5. Specifically, we add a carbon, but we end up with an alcohol. So again, a nice, easy way to do that is to take a aldehyde, right? So let's say that we had actually started this with this 4-carbon aldehyde group, right? So we have 1, 2, 3, 4 carbons. And we reacted this with a Grignard reagent, right? So 1, again, that would have added a methyl group to that carbon 4, and it would have turned this overall into an alcohol. So it's Grignard followed by water to give us this alcohol. Right, so now we're at the stage of 1, 2, 3, 4 carbons, but we've got a aldehyde at the end. So how do we get from an alkene to an aldehyde? So there are a couple ways that you could do this. First off, you could try to turn this into an alkyne, right? So to do that, you could say, okay, we've got Br2 and carbon tetrachloride, and then we've got excess sodium amide, 2, and then you've got water, right? So that would have taken this guy, it would have turned it into this guy. You could then hydrate that in an anti-Markovnikov fashion, and that would have tautomerized into the aldehyde. So to do that, that's the 9-BBN, and then it's the synonymous hydroboration oxidation reaction for alkynes. And so this was 9-BBN, and then H2O2 NaOH. That would have given you that. You could have also, at the same time, and I'll do this in a different language here, you could have hydrated the alkene in an anti-Markovnikov fashion, right? So if we had done, again, antimicrobial hydration for an alkene is just the BH3THF, and then 2H2O2 in AOH. You could have done that. That would have given you this guy. Again, 1, 2, 3, 4. No, I've made up a carbon, so that's not good. 1, 2, 3, 4. You could have then taken this guy and oxidized it to the aldehyde by using, because this is a primary alcohol, you would have had to have used the PCC and the methylene chloride. Both of these would have given you that. All right, so this is one of those situations where you've got multiple scenarios that are applicable and actually good solutions. And these would both be acceptable completely, right? So if you had taken the alkene and turned it into an alkyne, that would have been fine. You could have then, in an antimicrobial fashion, hydrated that alkyne to get the aldehyde. And then once you were here, you could react the aldehyde via our Grignard reaction to add in that extra methyl group and end up with the alcohol at the end. Alternatively, you could have taken the alkene, you could have hydrated it to form the primary alcohol, and then you could have oxidized that primary alcohol to the aldehyde. And then again, this one doesn't change at all. It has to be the same Grignard reagent or Grignard reaction regardless. So I'll go ahead and, I don't want to put it over the air because I'm not making good use of space. So there are two alternatives here. I'll go ahead and list them down here. We'll do the black first. We have bromine and carbon tetrachloride. 2, we've got excess sodium amide. And then 3, we've got water. So that was the alkene to alkyne. Now we're going to hydrate that alkyne. So 4, we've got the 9 BBN. And then 5, we've got the oxidation part of that, H2O2, NaOH. And then 6, we've got our Grignard reagent, CH3 MgBr. And then 7, we've got water again to protonate that final alkoxide. So that's one way. The other way I'll do in red. So first off, we hydrate the alkene in an antimicrobial fashion. So we have BH3THF. That's the hydroboration. Here's the oxidation. We have H2O2 NaOH. Once we have the primary alcohol, we're then going to oxidize it. So this is PCC in methylene chloride. Then that gets us to the aldehyde. So then 4 is the Grignard. And then 5 is H2O2. Not H2O2, H2O. So yes, technically it's like, 7 steps versus 5. I think to me these are both synonymous. You have changing a functional group, you got changing a functional group, you got reaction with that functional group to something else, you've got reaction with that functional group to something else, and then you've got addition of the carbon-carbon bond via Grignard reaction. So I think both of these are acceptable answers. Okay, so that's it. That's all she wrote. So that's all of the alcohol chapter. I'll upload this to right now, today. And then hopefully you'll be able to finish the homework. Okay, so email me if you have any questions. And then, yes, that's it.